Ever wonder how moons are born? For centuries, we could only look back at our own solar system and theorize. But now, for the first time in history, we're watching it happen, live, across the vastness of space. The James Webb Space Telescope, our incredible eye on the cosmos, has just given us a front-row seat to the birth of a new lunar system, and it's completely changing what we know about how worlds are made. So what exactly did Webb find? Picture this: 625 light-years away from Earth, in the constellation Chameleon, there's a young, massive planet named C Tycho b. This isn't just any planet. It's a gas giant, about 11 times bigger than our own Jupiter, and it's surrounded by a colossal, swirling ring of gas and dust. This isn't just a faint halo. It's a massive, structured disk, what astronomers call a circumplanetary disk. Think of it as a cosmic construction site, a moon factory churning out the raw materials needed to build entire new worlds. For the first time, we're not just guessing, we are seeing the very cradle where moons are born. This disk is so vast it stretches out for millions of kilometers, a swirling vortex of potential that holds the secrets to planetary formation. Webb's powerful infrared vision was able to cut through the cosmic haze and capture this structure in breathtaking detail, revealing a scene that, until now, has only existed in computer simulations and scientific papers. It's one thing to model it, but it's another thing entirely to see it. This is real, tangible evidence of a process we've long suspected but never witnessed directly. What's truly mind-blowing is what's inside this celestial factory. Webb didn't just see a cloud of dust. Its advanced instruments analyzed the chemical composition of the disk, and what it found was a rich, complex cocktail of molecules, the fundamental building blocks for moons. Specifically, the telescope detected the spectral signatures of gases like diacetylene and benzene. Now, these might sound like complex chemical terms, but what they represent is incredibly significant. These are carbon-based molecules, the very same types of ingredients that scientists believe were present in the early days of our own solar system. It tells us that the chemistry required to form rocky, and potentially even habitable, worlds isn't unique to our little corner of the universe. It's a universal recipe. This discovery is a game changer because it's the first time we've ever detected these kinds of complex organic molecules in a circumplanetary disk. It proves that these disks are not just inert piles of dust and ice. They are dynamic, chemically active environments where the seeds of future moons are being sown. The most exciting part of this discovery is how closely it mirrors our own cosmic history. Let's travel back in time, about 4.5 billion years ago. Our solar system was a chaotic, youthful place. A young, growing Jupiter was also surrounded by its own massive circumplanetary disk. Out of that spinning disk of gas and dust, our giant planet's most famous companions were born, the 4 Galilean moons Io, Europa, Ganymede, and Callisto. These moons are worlds in their own right. Io is the most volcanically active body in the solar system. Europa hides a vast liquid water ocean beneath its icy shell, making it a prime candidate in the search for extraterrestrial life. Ganymede is the largest moon in our solar system, bigger than the planet Mercury, and even has its own magnetic field. Callisto is a cratered, ancient world that holds clues to the solar system's early history. The disk around C Tycho b looks like a younger version of the very disk that gave birth to these incredible moons. By studying this distant moon factory, we are essentially looking through a time machine, witnessing a process that unfolded right here in our own backyard billions of years ago. It is like an archaeologist finding a perfectly preserved blueprint for a pyramid while it was still under construction. This gives us an unprecedented opportunity to test our theories about how the Galilean moons, and by extension other moons, came to be. So how does this cosmic construction project work? It all starts with the central planet, C Tycho b. Its immense gravity pulls in gas and dust from the larger protoplanetary disk orbiting its parent star. This material doesn't just fall straight onto the planet. Instead, it settles into a stable, spinning disk around it, much like water spiraling down a drain. Within this disk, tiny dust grains and ice particles begin to stick together. It's a slow, gradual process. First, they form small clumps, then larger pebbles, then boulder-sized planetesimals. Over millions of years, these planetesimals continue to collide and merge, growing larger and larger through a process called accretion. Eventually, a few of these growing bodies become dominant. their gravity sweeping up the remaining material in their path until they evolve into fully fledged moons. The detection of complex molecules like benzene and diacetylene adds another layer to this story. These molecules can freeze onto dust grains, enriching the raw material with carbon. When these grains clump together to form moons, they carry this carbon with them. This is crucial because carbon is the backbone of life as we know it. The fact that these building blocks are present so early in the moon formation process is incredibly promising. It suggests that moons forming in this system and others like it could be born with the essential ingredients for life already baked in. This discovery is about so much more than just one distant planet and its potential moons. It's a profound step forward in our quest to understand our own origins. For so long, the formation of our solar system was a story we had to piece together from ancient meteorites and computer models. We had the ending, but the beginning was shrouded in mystery. Now, with Webb, we can see the story unfolding elsewhere in the galaxy. We can compare the chemical makeup of the CT-CHA-b disk to the composition of comets and asteroids in our own system to see how well our theories hold up. Every new piece of data from this distant moon factory helps us refine our understanding of how our own planetary neighborhood was built. And it pushes us to ask even bigger questions. If the process that formed Jupiter's moons is common throughout the galaxy, how many other gas giants out there have their own families of diverse and interesting worlds? And this brings us to one of the most exciting implications of all, the search for life. For a long time, the search for habitable worlds focused almost exclusively on Earth-like planets orbiting in the Goldilocks zone of their stars. But discoveries like Europa and Enceladus in our own solar system have shown us that moons, especially those orbiting gas giants, could also be prime locations for life. These moons can be heated from within by the gravitational tug-of-war with their parent planet, allowing for liquid water to exist far from the warmth of a star. The discovery at CT-CHA-b shows that the raw materials for such moons rich in carbon are readily available. It strengthens the idea that habitable environments might be far more common than we ever imagined, hiding in the shadows of giant planets across the cosmos. We are living in an extraordinary era of discovery. The James Webb Space Telescope is not just showing us distant stars and galaxies. It's revealing the fundamental processes that shape the universe and our place within it. We are no longer just looking at the finished products. We are watching the cosmos build itself, one moon at a time. What other secrets are waiting out there in the dark? We're just getting started. Thank you so much for joining me on this incredible journey to a distant moon factory. If you're as amazed by the universe as I am, make sure to hit that subscribe button and ring the bell so you won't miss our next deep dive into the cosmos. Let me know in the comments what you think. Could one of these future moons harbor life? Until next time, keep looking up.